This video will continue our discussion of curvature, tangent unit vectors, and normal unit vectors by introducing something we call a binormal vector. Okay, so we have seen in 2 space, we talked about curves moving, but if let's imagine a 2 space curve, and everything we have so far, we have this like tangential vector, and then we have this normal vector pointing in which way. This is a good amount of information to describe a curve in 2 space, right? I can tell you where it's going and I can tell you where it's curving. Now, the problem is with just these 2 measurements is when we extend to 3 space, we have 2 different directions. We have things going forward, but there's more room to move. I have going forward and I can curve up and down in my 2 space, but now I can move to the left and right on my curve. So I have a twisting effect as well. So, we need something else. So what we could do is think about that this curve has a plane, T and N, right? Down here, we're still looking here. T and N has a plane that it lives in. If I stay in that plane, we could even think about putting this circle here and thinking about it like a disc rolling on the curve. It stays in the plane. That disc is moving this way on the curve, staying in that plane. But as soon as I go to 3 space, this circle that's moving along the curve could tilt towards you and away from you if you're looking at the computer screen. So I have that tangential motion moving me right or left in this case. I have N that's moving me up and down, forcing me to curve in certain directions. And then imagine a third vector pointing at you from this point here that is orthogonal to both T and N. That vector pointing at you, if you think about it, if it maintains that relationship between T and N, and think about it moving and it's sticking out at you, this vector that's sticking out at you would determine if it's pointing at you, it's still in the plane. It's still with this circle. But as soon as that arrow points down or up and not straight at you, this disk is moving out of the computer screen. Right? So as long as we stay in the computer screen with our disk, we're in 2 dimensions, but we need this third vector to describe if this disk moving along our computer screen is going to move at us or away from us, creating movements to the left and right or into the computer screen and out of the computer screen. We called this vector a binormal vector, and it makes sense that this vector should just be orthogonal to both T and N, because if T and N move outside of their plane, B is not going it's going to move with it. We could see the change. I'm hoping this makes sense. So we get this like 3, like a tangential, and then we'd have like a normal, and then coming out at you would be our binormal. So you can see that this creates almost like an XYZ, right? It's almost an XYZ. It has the same dimensions, meaning that there's a right angle in every corner, right? We get a right angle in that corner there. And then like this is movement going this way, right? It's like almost a plane with sticking like a wing and a tail wing going up or something. I don't know. But that binormal vector is just an orthogonal vector. Now, since T and N are unit vectors and I cross them, B is going to also be a unit vector. All right, so all 3 of these are unit vectors. T is pointing in the direction. N is pointing in the direction it curves, and then B gives me indication, is it turning? Is it moving left and right in 3 space? Okay, so with that formula, we know now we can find the binormal vector by just crossing T and N. It is a unit. We can also notice that T and N form a right-handed system. Everything follows the right-hand rule with that. The big thing here, if you want to Google this topic, this is the T and B frame, the tangential, normal, and binormal frame that will tell me 3 different directions given myself on a space curve. I imagine, like, and I said this in a former video, I think this would be very helpful for video games, moving in a 3-dimensional world, but I'm also not a programmer. I'm just speaking at what I think it looks like. All right, so we can talk about the rate at which it moves out of that plane. The rate comes about, okay, so it would be the rate as B changes along C, so we could talk about B changing with arc length. Okay, as B changes with arc length, that would be the rate at which it twists out of the plane. So short calculation, let's follow this formula. We know B is t cross n. So if we take the derivative of b with respect to s, we could just replace b with t cross n. Then we can follow that is a product rule. Given cross products, I take the derivative of this times the second, and then I take the first one times the derivative of the second one. This, by definition, is equal to 0, right? They are parallel. They run in the same definition by definition. You can see that down here. That's just by a definition that we came up with. 1 over k, or kappa, is curvature. So we see that they are scalar multiples of each other, which means that they are parallel. Okay, so that if they're parallel, 0. Okay, so that's 0, and we're left here. So notice by definition that we have that, so we get that. Therefore, the cross product is 0. We're going to move forward from this. Okay, so I know the rate of change of binormal with respect to arc length is equal to the cross product of tangential and the derivative of the normal vector with respect to arc length. Okay, a couple of these things become clear. dB ds is orthogonal to both t and d normal with that because it is the cross product of t and d and ds. We can see that on this. This is what we're getting from here. Oops. This is equal to that. So we can see that since they are the cross product of those two, then the answer of a cross product is always orthogonal to the terms being crossed. dB is also orthogonal to b. Right? That's by definition of that. We talked about that in a previous video. And then dB is parallel to n. The last bullet leads us to this definition of what we call torsion. Torsion is the rate at which a curve twists out of the Tn plane, the tangential normal plane. So it's like how fast does it go? So using that last bullet that is parallel, then that means that dB ds is some scalar multiple of n. So we call it tau there. So that is the torsion. So the magnitude of torsion equals the magnitude of dB ds, which is the rate at which the curve twists out of the t and t plane. If we take now this equation and I multiply both sides by n, we're here. Dotted, both n. N dotted with itself is a 1, right? They're unit vectors, that's why, right? Think about the n dotted with n is just the magnitude of n squared. Well, the magnitude of n is 1. 1 squared is 1. Leaving me here, right? This leads me to my last formula. If I multiply both sides by a negative, we got that. All right, so in some interpretation of our picture here, so we have an oscillating plane. That is the blue plane right here. That is where osculating, that is where that plane exists, where that wheel is rolling. You can think about that radius curve, a circle being in there moving along the curve. All right. The normal plane would be the in and binormal plane where they intersect, so it's the green plane here. This would be what the circle's moving in and out of, going towards that, or not in and out of, but leaning towards being perpendicular with that. Okay, so the torsion, which is equal to the magnitude, gives the rate at which the curve moves out of the oscillating plane, and then also in a complementary way, the curvature, which is equal to that, gives the rate at which the curve turns within the oscillating plane. So, like we have some circle rolling along this curve in that blue plane, and the rate at which it leaves the blue plane on either side would be your torsion, given by this formula. Okay, let's give an example of this. Consider the circle. So we have this circle here. We can see it's a circle because it's cosine sine in each component. So that tells me it's a circle, and then the 4 is the radius. So without doing any calculations first, let's try to find the binormal vector b and determine the torsion. Okay, so if I look at A, here's my picture. That's how we're going to do it. It's a circle. We know torsion goes out this way. Makes sense, it's moving. And then remember, n points in the way that it's curving. So they're both flat like that, which means, remember, our binormal vector is determined by the cross product, which makes them orthogonal to both. So we literally have b just pointing in the direction of z. All right, so that means, and remember, b is a unit vector, so the binormal in this case is actually just equal to k. And that's because it's pointing straight up, and it's a unit of 1. So, because b neither changes length nor direction, if I take db ds, all right, it doesn't change. It's the same all the way across here. It's never changing. It's always pointing straight up in the unit of 1. We can see that any point here is going to give me that same scenario of a unit vector pointing straight up. So it is a constant, so that means the derivative of that would be a 0, which means that tau, or torsion, however you want to write that, is 0. I think it curves in. Am I going the wrong way? Nah, it's about the same. I'll be able to know what you're talking about. So that's A. And then B, use the definition of B to calculate B and confirm your answer. So remember that it is, we got to find our tangent, not prime. It's a bad habit of mine. Which is r prime over t divided by its magnitude. All right, so let's find r prime of t. We have negative 4 sine t and then 4 cosine t. We're going to need a third component because we're going to cross these things, so we'll just call it 0. We're going to cross, and eventually we're going to cross that. So we have that. We need its magnitude. Taking its magnitude to save us some time, the answer is 4. Right? If you square those, the sines and cosines are going to go away with the Pythagorean identity. So there's that. So the tangential vector is negative sine t, cosine t, 0. Right? There's that. So now we also want to find the normal unit vector, which is going to be t prime of t over its magnitude. All right, t prime of t is negative cosine t, negative sine t, 0. And that's going to be divided by t prime, its magnitude, which I have just there, and it's a 1. All right, so there's my normal. So to find my binormal vector, I'm just going to cross those two vectors. So negative sine t, cosine t, 0. And I'm going to cross that with negative cosine t, negative sine t, 0. All right, to save some time, I'm just going to do this cross the algorithm. You can use the determinant stuff to figure that out. If I cover up the I column, I'm going to get a 0i. If I cover up the j column, I'm also going to get a 0j. I'm going to just make a plus. And then if I cover up my k column, okay, so I'm going to get sine squared plus cosine squared, so I'm just going to get a k. This makes sense, right? That's what we were expecting, is that b equals k. All right, we're going to do one more example of finding torsion. This one's going to require a little bit more work, so I can model that for you. Okay, so we have this helix, and they want us to measure the, it says compute the torsion of the helix. Okay, so first thing we're going to have to do is find our t. So t of t. All right, that is going to be r prime of t over the magnitude of r prime over t. So I need r prime. So r prime of t is equal to negative 2 sine t, 2 cosine t, and then 2 pi for that last one. All right, the magnitude of that vector. All right, we're going to get we're going to square that. We can factor out a 4, so I got 4, the square root of 4 plus 4 pi squared. There we go. All right, not the prettiest thing in the world, but we could still do it. I got 1 over that thing. There we go. Okay, so that's t. We also need n. All right, so n is t prime of t over the magnitude of t prime of t. I'm going to help you out on this for the sake of video because that's going to take some time. That vector is going to be negative cosine t, negative sine t, 0. So if you'll just trust me on that one, because if not, we're going to have to, hold on, I'm checking something real quick. Cool. It looks like it all lines up. Great. All right, so to find we got to find our binormal vector now. It's going to be the cross between those two. I know I can take that constant out of my cross, right? And then I'm going to go ahead and cross those. So I got I, J, K. I'm going to show you to set this up, and then we'll go ahead and figure it out. I'll help us out. All right, so B is t cross n, so t is negative 2 sine t, and then 2 cosine t, and then 2 pi. And then the other one is negative cosine t, negative sine t, and 0. If you work all this out, we are going to get 1 over that constant times, and then the vector that we're going to get left with is going to be 2. Hold on, I lied to you. It's going to be 2 pi sine t, and then negative 2 pi cosine t, and then the last thing we're going to have is negative 2. Or positive 2, sorry. There we go. Let me double check this with my work. I want to make sure I don't lead you astray. Cool. So that is our binormal vector. I saved you some work here, but you should go do that to confirm it. It's really not terrible. It's just a lot of algebra. It just becomes alphabet soup at some point. Okay, so the next thing we need to do is determine dB/ds. We have the binormal. Remember, our goal is torsion. Our formula for torsion was t equals, okay, let me grab this, negative dB, that's a binormal vector with respect to s, times, and then the other thing was the normal vector, unit normal vector. Okay, so we have that formula. We're trying to find dB/ds. We're going to use what we did a second ago in one of the theory parts, that we can use the chain rule here to do like a dB dt times dt ds. We also have the other way where we could do t's as well. All right, this is actually dB/ds. I can rewrite this thing. dB dt, I can actually write this as dB dt, and then this is going to be the little weird part, ds det. I'd flip it over, right? So we have that. So I just need to find these things here. I need dB dt, which we can do, right? We have that vector, we can do that. And then also I'm going to need ds dt. So I think we should do maybe, what should we do first? Let's go ahead and do ds dt. All right, ds dt. How we're going to do that is by definition. I know that ds dt from a while back is equal to the the magnitude of r prime. This goes back to our arc length section. If you take a look at that, we got to this result. So I have to take the square root of r prime, which was right there above. How this is going to work is I'm going to get a 4 times sine squared t plus cosine squared t, and then I'm going to get, where's that r prime, 2, so I got a 4 pi squared. So the magnitude, oh, we already did this. doing work that we've already done. Okay, so we already have that right above. I'm going to erase this and put that there. It's a square root of 4 plus 4 pi squared. All right, so we have that. Then we also need dB dt. And we can use our definition, dB ds. We can use the definition that we just came up with here. Okay, so I need dB dt. All right, and it's going to be over that. So I got over 4 plus 4 pi squared. And then I'm going to throw the derivative of that. I keep my constant out front because that's going to help. And I'm going to throw that through and try to take derivatives with that. Then I take the derivative with respect to t of each component. Derivative of sine is cosine, so I get 2 pi cosine t, comma, okay, and then 2 pi sine t. And then that was in the end, I think it was a 0. No, it's a 2. Okay, so in this case it would be 0. So dB ds, things work out for us. We get 1 over, the square roots are gone here. I'm going to have to make my work smaller. Forgive me, to make room. The square roots are gone, and then I got 2 pi. We could even factor out that 2 pi if we wanted to. Let's do it, 2 pi. And then it's times cosine t, sine t, 0. So that's dB ds. So our last thing, let me shrink this up so I have room to write. Okay, is torsion is equal to negative dB ds dotted with our normal vector. So the negative of that, throw a negative 2 pi over 4 plus 4 pi squared. All right, times our normal, or dotted with our normal, which is negative cosine t, negative sine t, 0. So torsion is equal to, okay, so it's going to be negative 2 pi over 4 plus 4 pi, and then I'm going to do the, it's not a vector anymore, so it's going to be times, let's get rid of all our negatives. So this just goes through. Oh, I never put, okay, forgive me. Go back. Forgive me. Okay, we're dotting. We need 2 different vectors. So these vectors are, I wrote down in for that beginning. So we get negative dB ds, so it's negative 2 pi over 4 plus 4 pi squared times cosine t, sine t, 0, dotted with the normal vector, which is way above, negative cosine t, negative sine t, 0. All right, so if we dot that, okay, it's going to be the negative 2 pi over 4 plus 4 pi squared. And then I'm thinking about dotting. We're going to end up getting a 1. So we get 2 pi over, and then did our negative cancel at all? The negative can go through. Oh, we need the negative to go through here, actually. Let's put the negative, instead of there, let's put the negative here. And then notice that actually works out to 1. Because if not, it wouldn't have been negative cosine squared and negative sine squared. But I need that negative to both be there. So my torsion is right there. Right? I could take that 1 and take it off if I wanted to. Okay, so we have that. We could use other formulas here. There's other ways. So I'm going to list this for you in one spot. So here it is, if you'd like it. I also, most of the time, this is stuff that could go on, depending on what kind of test you're taking. With me, mine change semester to semester. This would be a good thing maybe to have all in one place, or take with you to the test if you're allowed to do that on this in this semester. Whatever this semester looks like, this would be a good thing to have all in one place narrowed down.